Good morning, everybody. On behalf of TechForum, I greet you all, welcome you all. And today's speaker is Dr. Shashikala Gangal, who is going to touch a topic on Nadi Pariksha, that is something to do with Ayurveda first. And I would like to hand over the mic to Mr. Surendra Agarwal, who will introduce her. Thank you.
Thank you. Dear participants, a very good morning to all of you. I am pleased to welcome Dr. Shashikala Gangal. She is the team leader of Academia Research Group, which is doing innovative work in the field of Ayurvedic medical devices. Dr. Gangal is ex-ISRO chair professor, ex-professor and head Department of Electronic Sciences, Savitribai, Phule, Pune University. She has 44 years of teaching experience, including 36 years of research experience. She has won many awards and has developed many equipments and instruments. Has published 105 research papers in national and international journals. Is author of textbook on communication electronics for IGONU. She has handled 28 research projects sponsored by different agencies. Today, Dr. Gangal is going to speak on Nadi Pariksha, something very, very important part of the medical devices of Ayurveda. So over to you, Dr. Gangal.
Thank you, Dr. Agarwal, for kind introduction. I'll be now start. Good morning to everybody. I'll be giving my information about what research I have done and what is necessary to do in this particular problem of Nadi Pariksha to making it objective. And I think I will be able to convince you that this should be taken up further. Diagnosis according to Ayurveda is to find out the root cause of disease. It is one of the 8 important examinations which Ayurveda people do. By examining this nadi, Ayurvedic physician finds out the predominant dosha. There are 3 types of doshas, Vata, Pitta and Kapha, and they are related with the Panchamahabhuta, earth, air, water, fire, and other things. So Vata particular is the combination of earth and air. Pitta is fire and water. Kapha is water and earth. So this Nadi Pariksha, as you can see from the figure given down, Nadi Pariksha is done at the root of the thumb by examining the radial artery. And there are 3 points on this finger and the of Nadi where you feel the Nadi. And Nadi Vaidya uses his 3 fingers and their positions and the pressure on the radial artery to diagnose the patient. Now, presently, this technique, of course, is a subjective, and the accuracy of the diagnosis depends upon expertise of the expert or Nadi Vaidya. And this is a small exercise. This we started long back, and of course, after that, an instrument called Tarangini it's developed and it's in the market by Dr. Aniruddha Joshi from IIT Powai. Now, so this we also started in the similar time, but of course, from being from the university and not having enough funds to patent it or to manufacture it, this remained in the research process only. But still, there are lot many things which can be done in this direction. Arterial pulse looks like this. It's a systolic peak and diastolic peak. And this is felt at it's a regular throbbing of the arteries. And this is caused by the successive contractions of the heart. This pulse pressure is typically in the range of 30 to 50 millimeter of Hg. It's 5 to 6.5 kPa. Pulse rate is typically 1 to 1.67 hertz. That is 60 to 100 minutes per minute for a healthy person. But along with this, when you go, we are going to make it objective or sense it by the sensor. We get the noise signals, and these two noises are there. One is the respiration frequency, which is between 0.2 hertz to 0.3 hertz, and AC mains, because we are the receivers of the receivers and the overhead wires. Now there are not many overhead wires in the cities, but in the outside the city there are many AC mains wires, and they transmit 50 hertz. And we are the receivers, and that signal, when the sensor is sensors are touched to the uh, hand, this signal is also available in the pulse output. The Vata, Pitta, and Kapha have these three have different characteristics, locations, and they typically there are three gatis associated with these pulses. One is Vata pulse, it moves like cobra. I was shown it uh, I mean the standard waveforms over here on the right side. Pitta pulse is typically moves like a frog, and Kapha moves like a swimming swan. That Nadi Vaidya, he feels that, and he diagnoses whether it is Vata dominant, Pitta dominant, or Kapha dominant. But there are a lot many variations of these uh, three, and that he like the senses through is changing the pressure on the sensor, and there are around 72 variations of these nadis. When we talk to Nadi Vaidyas, they say so. But a good or a best uh, Nadi Vaidya, he can till now at least, 22 of them could be sensed by the human being. And therefore, to increase the accuracy of diagnosis, we need to take the pulses and analyze them in different ways to get this particular uh, information. The pulses are also classified on the basis of depth of the pulse, intensity of the pulse, amplitude of pulse, frequency, rhythm, length, quality, quantity, and texture and width. But we require sensors for sensing it. These are dynamic pulses. And when a Nadi Vaidya touches your wrist, he also gives pressure from his fingers. So it is a static pulse dynamic pressure. And therefore, the static pressure should not affect the pulse sensed by the sensor. And therefore, the sensor should be piezoelectric. Otherwise, piezoresistive also can be used, but they sense the static as well as dynamic pulses. The sensor should be flexible. That should be useful for any shape and size of the human wrist. Sensing area is typically 8 to 4 millimeter with a tip of your finger. High operation bandwidth is necessary. Pressure range is 1 kPa to 10 kPa. It includes the pressure range of the nadi. The resolution should be 0.2 kPa. Sensitivity is 120 millivolts per kPa. Is expected. Response time should be less than 20 milliseconds. Frequency response should be constant up to 20 hertz, because beyond 20 hertz we don't get any V1 pulse. It is actually 1 to 1.67 hertz. Low acoustic impedance should be there, because it is also can be heard. The sensor should be biocompatible and chemically inert. There are few available which we used in our experiment, was MLT 101. This but it is hard, and therefore when you press these sensors on your wrist, then the patient may get hurt, and therefore we require a flexible material like polyvinyl difluoride, which we selected for development of our sensor. This PVdF is polyvinyl difluoride. It's a polymer having a piezoelectric coefficient. It should be large because we need to get a very feeble pulse also should be detected. It should be flexible, high operation bandwidth, low acoustic impedance, biocompatible. It is chemically inert, and it can be easily fabricated in the form of films and other shapes. We developed sensors using these PVdF films. The chemical formula is CH2CF2. And this is semi-crystalline polymer. This can exist in 5 different phases: alpha, beta, gamma, delta, and epsilon. But the piezoelectric sensitivity is higher in beta phase, and therefore we need this polymer PVdF in beta phase. And this can be to get the beta phase PVdF. We can do physical deformation, that is stretching or spin coating, electric pooling, quenching, and composite. You can say that you can ask me that whether it is available commercially, this particular polymer. It is available, but you have to get it tailored because the PVdF films are used for different purposes. And if you have to get for this particular pulse, the thing, you need to get a beta phase. And this becomes very expensive, at least for the people like people in the research this thing. You cannot purchase a single sheet, because for our research we may use the single sheet. But the commercially it is available in bunch, maybe 2,500 and all. And if it is of a particular phase, then it becomes more expensive. And therefore it was not possible for us to purchase any. And the purchasing process is also very long. I mean, it takes 6 months or so for getting all these things. And therefore, our 6 months, if project is not done, then we get banging from the funding agency. So we thought of developing it or converting the available PVdF crystals in PVdF film with a beta phase. In the present work, we used spin coating and pooling techniques for getting the beta phase PVdF. We developed this PVdF-based pressure sensor using the films developed, and we compared our sensors to with the commercially available sensors for validation. The preparation parameters are the PVdF crystals are dissolved in DMF, dimethyl formaldehyde, and secondly, it is between, because it is the viscosity of the solution and the dissolution rate, etc. They are very slow. We added acetone to it. Weight percentage for deciding the viscosity of the material, we changed 16, 20, and 24 weight percent. DMF plus acetone ratio, we varied between 80-20, 60-40, and 40-60. Stirring time, stirring temperature was 60. It cannot dissolve in at room temperature or takes very long time. Therefore, we increased to 60. Spinning speed was varied between 500 to 4,000 RPM, and spinning time was varied between 30 to 5 minutes, 30 seconds to 5 minutes. Baking temperature after converting into a film, we use to dry it or the baking temperature to change the structure of the film. We varied between room temperature to 90 degrees. Effect of these parameters on the film thickness, beta phase contents, and morphology was studied. And the films, we required the films of the thickness of the order of 13 to 15 because they should be handleable. Maximum beta phase to have a good sensitivity, and the sensor should be pinhole free and uniform for getting the best result. We did this all these thing using the structural, physical, morphological characterization of the material and film. This was done using thickness was measured using macrometers few ways. FTIR, XRD, and SEM. XRD gives the structural chemical structure. SEM gives the morphology, and tensile stress gives it the strength of the film. These are some graphs. I don't think we should go into details of it, but this thickness variation with spin speed, then as the thickness of the film with the DMF acetone ratio, then beta phase fraction variation with spin speed, beta phase variation using baking temperature, etc. We studied. We took XRD. We took we have taken morphology, effect of baking temperature with a. Finally, because of the thickness requirement, we did not require very thick films. We required thin films, and therefore 16 weight% 16% solution was used, and we get around 13 micrometer thickness maximum using this, and that was enough for our pulse measurement. So we took that. If you see at different baking temperature, you get different porosity and different uniformity of the film. So using all these data, DMF acetone, it was very, pinholes were there with a 16 spin per weight% spin coated films baked at different temperature. So we used the solution DMF acetone and that to 40-60 ratio of DMF acetone and 90-degree this baking time, which gives us sufficiently uniform film and pinhole free film. Tensile testing was also done. And so the optimized parameters of these, preparation parameters were solvent concentration of 16 weight%, DMF acetone solvent mixture ratio was 40-60%, spin speed was 2000 RPM, baking temperature 90 degrees, beta phase fraction 55 degrees, tensile strength 53 MPa. And these parameters we used for making our films, PVdF films, and we could do it successfully from batch to batch. Transparent, these films were transparent, non-porous, with the thickness of the order of 13 ±1 micrometer per optic. After this, the beta phase was not very sufficient. It was still, the sensitivity was less, and therefore we poured the films using electric pooling to enhance the piezoelectricity of PVdF film. This gives a permanent orientation of the molecular dipoles in the direction of electric field. And therefore we use this, this was a holder for PVdF film for electric pooling, and we applied a high voltage or the high electric field of the order of 125 megavolt per meter is applied across the electrodes at 100 degrees centigrade for 3 hours, and the voltage was removed after the film is cooled at room temperature. And this gives a beta fraction was increased to 65% from 55%, and thickness was increased from 216. Thickness of the film was increased, but this also is okay for our pulse measurement. Pulse taking. This polling voltage versus D33 graph is shown over here, and the piezoelectric coefficient of this films were about 18 picocoulomb per Newton with the polling voltage of 125 megavolt per meter. Using this we measured using a piezometer system, which was purchased through the research project. Then this, of course, this 16 micron film is very flexible and it cannot be handled nicely, and possibility of tearing it, and therefore we encapsulated it in a PDMS. The PDMS thickness should be such that the pulse which is sensed by the PDMS as well as this, the pulse amplitude should not decrease. Otherwise, this PVdF films are of no use. Therefore, the PVdF film was a single film we required or for putting it on the pulse point is 20 millimeter by 18 millimeter. It was cut in a 3 parts of the size 4 millimeter by 18 millimeter. 4 millimeter is the width and this length, which will be put on your wrist. The films are encapsulated in PDMS layer of 200 micron on each side using a mold fabricated using aluminum steel. These 3 films were simultaneously covered, encapsulated using PDMS because we want that the thickness of the PDMS also should remain constant for getting a constant, same response from all these films. Then we put this on a sensor housing. So this is the area, 8 millimeter. This depth is 2 millimeter because the movement of the this PVdF films will not be more than 2 millimeter naturally, and therefore we put it. This gap on the holder was 2 millimeter, and it was PVdF film encapsulated was put like this, and in a group, a thin metal sheet was for the contact. Then we put that on the copper clad, and we screwed it over here. And this sensor, this was a typical how we got the contacts and all the details are given over here. And the screws, etc., were little difficult to handle, or say they may tear off the film, and therefore we used PVdF, adhesive PVdF tape for having a. This is another housing which we made, and this is the final mold of our PVdF sensor. This is and then we connected this cable, and this will it's GNC connector, which will be connected to your measuring instrument. We tested these films for the response for the different dynamic pressures from 0 to 10 kPa and at varying frequency range from 1.5 to 20 hertz, how they will respond and what is sensitivity. So this we use a load cell for testing the pressure. This is a sensor, a load cell is put on it, and the solenoid vibrator was used for giving the pressure on the sensor for measurement. So we met all these electronic gadget or for the solid pulse generator for solenoid driver, then load cell. A dynamic pressure was given to a pulse sensor. The load cell and the pulse the sensor output was given to a signal conditioning circuit, and it was the data when the output was taken on a PC through a NI DAC card. This is a solenoid driver. This is a load cell signal conditioning circuit, and this is a PVdF sensor signal conditioning. Here we used low pass filter, high pass filter to avoid the respiration frequency, which is around 0.2 hertz or something. So it's a high pass filter, and a notch filter was used to avoid the 50 cycle pickup, which is taken by this pulse sensor. This is our data LabVIEW programming. Through LabVIEW programming, we developed a 2-channel data acquisition system. This is a block diagram of that view of the program. This 2-channel data acquisition system with a which can do data selection, peak detection, pulse selection can be done, which the best pulses will need to be taken, because maybe in the initial stages, if there are pressure changes, the stable pulse may not be available, and therefore pulse selection, peak detection, etc. were made. This is a average response of 3 sensors, because we wanted the 3 sensors to be of equal characteristics. So this is the pressure response and the output voltage. All the three sensors response is shown over here. Then the linear regression was taken, pressure versus the output voltage, the linear characteristic. And the frequency response of all the sensors lies in the same, same range or almost equal. So up to the 2.5 kPa PVdF sensor output increases linearly at the rate of 0.3 volt per kPa, and above 2.5 kPa the output increases linearly with a pressure at the rate of 0.62 volt per kPa. But we are interested in the low range of kPa, so it's fine. Output of the PVdF sensor is linear with a correlation coefficient of 0.99, and the sensitivity was around 0.62 volt per kPa. After dividing by the gain, the sensitivity of the sensor was stated as 0.212 volt per kPa. Frequency response of the three sensors was constant up to 20 Hertz, and therefore they are suitable for pulse measurement. Then we wanted, the Nadi Vaidya initially puts his fingers on the Nadi on 3 points with an equal pressure. And for checking the accuracy of the, to make his diagnosis more accurate, he changes the pressure on the different points. Maybe on Vata he will increase and he will leave the fingers on the other two. And therefore we developed this system. It looks clumsy. Finally, we would like to go for a robotic hand, which can do all these jobs with in a very small place or the very handy equipment. So these are three sensors. We put load cells on it to see whether the pressures are put on the wrist are equal and all that. So rack and pinion assembly was used to change the position of change the pressure on the pulses. So we had put it on the wrist of the person with all these load cells. This is our signal conditioning sensor and a DAC card, and the output was seen on your TV screen or your laptop. This is the power supply for it. So this is the 3-channel data acquisition system. This shows the pressure which is given on the pulse so Vata, Pitta, and Kapha. That at 3 points, this pressure was measured and displayed from the load cell, and this is the pulse output of a particular person. So this is a 12-bit portable NI DAC. It's used to acquire the data, and it was shown on the page. You can see that from the same person's hand, the 3 pulses at 3 pulse points are different. They are having different amplitudes. They are having different shapes. So we took whether this frequency contents of these pulses are same. We took a FTIR, Fourier transform of the pulses, and we have seen that the sensor 1, sensor 2, and sensor 3 has the same frequency output. So the frequencies of the pulse is same. And this is the pulse sensor output from MLT 101 sensor, which is commercially available. And this also shows the same frequency response. So to validate our sensors with the available commercial sensor, we did this exercise. Then to see the data simultaneously, regularly, and we can select some of them and you can magnify them, the pulse selection, and see the more details of the pulses. The selected pulses are of this type. This is FFT of the, and all these things you can do using the same. The program was developed for this purpose. Then we took the pulse data from 30 subjects in the age range of 22 to 25 age. The pressure which was applied to the individually on 3 sensors was 4 kPa, and the same pressure was applied to all the 3 sensors. And data was acquired and stored in the PC for further analysis. We have taken, at the same time, we were having Nadi Vaidya present in the for our experiment, and he was also diagnosing his diagnosing or seeing the Nadi or checking the Nadi, and we were interested first only in whether it is Vata dominant, Pitta dominant, or Kapha dominant, because other things, other disease diagnosis is a very long way to go. So we, simultaneously the Nadi Vaidya was present for the experiment. So analysis of the pulse, we took the amplitudes of the different pulses like this. Whether which type of, whether Vata is dominant, Pitta is dominant, or Kapha is dominant. That we, check from the amplitudes of the pulses. So highest amplitude pulse point for 18 subjects or 18 patients was Vata type. 3 patients were of Pitta type and 1 was from Kapha. And you normally get Kapha people very less. 4 of them were Vata, Pitta, and Kapha. All amplitudes were same. And these patients, and it indicates that these patients were healthy. Vata, Pitta dominant were 4. So this disease may be there in all these, but these 4, if the amplitudes are same of Vata, Pitta, and Kapha, the patient is diagnosed to be healthy. This as I said, the dominance of the dosha is not also confirmed from the Ayurvedic person. So Vata dominant pulse looks like this. Vata is iron. Pitta dominant has Pitta. From patient to patient, the amplitudes may change. So these amplitudes may not remain same from patient to patient, but relative amplitudes are seen to see whether it is Vata dominant, Pitta, or Kapha dominant. This Kapha dominant is this person, and Vata, Pitta, and Kapha pulse is like this. All the amplitudes are. This software which we developed has been made to develop pulse analysis software to extract parameters from the pulse. In LabVIEW program, one can import the pulse data. Pulse rate and its variation can be measured and visualized. Pulse parameters like time to the peak, time between systolic and diastolic peak, peak height, peak area, width of the peaks at different heights. All these things can be measured for further analysis. FFT analysis can also be carried out using the software, and data we normally store in the Excel file format. Now, in order to validate the system performance, further pulse data is collected from the subjects in the age range of 20 to 55. So as I said in the previous slide, amplitude, pulse rate, frequency, FFT, the change in the waveform shape, length and angle of deviation of the percussion wave was done using the program. And we also measured rise time, fall time, area under the curve, distance between systolic and diastolic peaks, amplitude ratio of systolic and diastolic peaks. And all these things were taken and stored into the formula. The area under the, or the width and at different heights of the pulse also were taken and stored in that patient's data file. So these the data from 20 to 55 age people we collected, and we measured the distance between systolic peak and diastolic. This is time t1, and the whole pulse time is t. So we took the ratio of t1 to t of these different patients to see whether what happens is if the person is aged, its artery becomes stiff, and therefore this pulse position, it can be shown through the systolic and diastolic peak positions. And so distance between the pulse of the systolic and diastolic peak versus age was done. Of course, this is a very random data. It indicates that we require to take the data from large number of people and to see whether but the variation is, as you go on increasing the age, the T1 to T ratio decreases, meaning that this T1 is smaller and the systolic and diastolic peaks are coming nearer to each other, which is normally in the older people. So we also took width at 75% height of the peak versus age, and that also showed some variation. But it is very necessary to take large amount of data, because see that the arterial stiffness may not be only due to the age, but arterial stiffness may be due to some other disease. So the same effect will be the same, but the cause will be different. And therefore, if you, say if you take a disease blood pressure, and the blood pressure can develop in a person due to different reasons, and therefore his nadi may be felt differently. So you cannot say that if the amplitudes of or the amplitudes or the positions of the systolic and diastolic peaks, etc., are in this range, you have a person with a blood pressure. It can be different, and therefore we need to group the data to see the similar patients group, similar type of similar reasons for getting the blood pressure, and then we can finally train our program or train the computer to say that to diagnose it automatically. So for diagnosing automatically without the help of Nadi Vaidya, you require to have a very large amount of data. And so this we have, so we can say that we have shown the feasibility of developed PVdF-based piezoelectric sensors and Nadi Pariksha-sensor for human pulse detection and analysis. It was demonstrated successfully. Now, work which needs to be done for disease diagnosis actually. This process is double blind, because even if we say that our pulse data, Nadi Pariksha Yantra is successfully done, but we do not know how these pulses can be diagnosed, and Nadi Vaidya doesn't know how to interpret these pulses. So it's a double blind, and therefore we have to educate each other to get the best result of this Nadi Pariksha. so we need to collect very large data, and we require minimum 3 Nadi Pariksha-sensor, which can be handled by 3 different people to collect the data from different uh, places and different age groups, different diseases, etc. For this, robotic hand is necessary to simulate the Nadi Pariksha. The Nadi Vaidya examines the pulse first by giving equal pressure on the 3 pulse points, and then by changing the pressures given on 1 or 2 pulse points alternate. So we want to address initially only 2 very commonly available, blood pressure and diabetes, the diseases. I mean, through the though the disease is one, the like blood pressure, the reasons may differ from patient to patient, and we need a Nadi Vaidya in first from Nadi Pariksha, but we need to translate that his Nadi Pariksha into the objective, into the pulse parameters. So, as I was telling, there are 72 type of nadis, and Nadi Vaidya experts till now could diagnose only 20 to 22 types. So, this requires a pulse data from large number of patients, large number of groups with similar diagnosis by Nadi Vaidya and its analysis. And statistical analysis of all these collected data is needed to get the exactness of the diagnosis. We approached with our long back around 2012 or 13, Ayush. We were involving CDAC, which was present on the university campus. For statistical analysis, they had agreed. They had doctors also, who were interested in such conversion of subjective technique to objective technique. But I don't know, the Ayush funding agency people, they visited 2 to 3 times, but finally did not happen anything. And because of lack of funding and lack of manpower for this, we had to keep our further research pending. Which we academicians normally have following problems. Appointment, though we have a good research project funded by the funding agency, appointment of a suitable researcher, it takes around 3 to 6 months for getting. And further, now there are limitations or the restrictions on the researcher, that you have to have the researcher from a particular category, which he or she may not be interested in this type of project, and therefore the project suffers. Availability of the material and the delay in purchasing, which I told you little before. Difficulty in getting small parts fabricated in the university workshop and or outside, and therefore there is a delay in machining. And though we science people, we do not have an engineering mindset, and therefore we get something done, the person fabricates something else, etc., etc. A lot of time goes in that. So the engineering of the developed equipment is our limitation. We cannot do it, and though we do it in time, the research or timely research, it's very difficult to apply for the patent, because we do not have enough funding. Now it is little relaxed, but when I was doing all this work, the patent application, the students, and by the time we get a patent application written and patent application done, the student gets frustrated and he goes away. And therefore, it's difficult to do any patent also. We do not have sufficient funds to do that. So these are some of the problems which we face, and therefore, though we start the topic very timely, we cannot end it in a successful product as such in the market. Thanks a lot.
Thank you very much, madam. I can ask now audience to start with the questions if they have. They can now ask any question if somebody wants to.
Yeah. SP Bhatnagar.
Yes, sir.
Can I ask?
Yeah, you can continue.
Yeah. Thank you, ma'am, for nice presentation. I just wanted to check the commercial equipments which are being manufactured now. What kind of sensors are they using? Are these the same sensors which you developed, or they are using?
Actually, I'm not. I did not get that information from their website, which type of sensor, because they have a. So the details I'm not having. That currently which is available in the market.
Not disclosed actually.
Okay. Yeah, they are not disclosed that.
Right.
They also have said that they have done some 2-3 sensors, some few sensors, types of sensors they did. It's a piezoelectric sensor only, but I don't know what material and what thing they are.
Okay, thank you.
You have actually said about it's a kind of load cell only, no?
Yeah. Huh?
You said it is kind of load cell only, load sensor.
Yeah. The load cell we use for characterizing this sensor.
Okay.
For characterizing, I mean, whether how much pressure gives how much output, etc., etc. To know its sensitivity and all this, we use your load cell.
Yeah.
And to give the equal pressure. I mean, once we have all these things done, we can eliminate the load cell. Once we have it.
There is some force sensors are also available for this range.
The force sensors will not be.
Okay.
Will not be useful.
Okay. I'm using in this range kPa sensor, 10 kPa up to 10 kPa sensors. Okay, but there are all MEMS technology, based on MEMS technology.
Yeah, I would like to give you some information that our fingertip has number of sensors. Okay, and we have a future plan. Since I was also working in MEMS, I had a thing in mind that all these small pressure sensors or piezoelectric sensors can be fabricated in the MEMS form. So there will be large number of sensors on the. I mean, we can simulate this large number of sensors on the tip using a MEMS device.
Yeah.
So a MEMS device can be put on the 3 fingers or as 3 fingers, and that will give you, because what happens is wherever the sensor is touching nicely. Okay, if somebody is having a very hard bone, may not be. It may bend, or it may give some different sensitivity also. Yeah. So, and what Nadi Vaidya sees that he has many sensors on the tip, on the fingertip. Yeah. Yes, so he can get its exact information. So to simulate that, a number of small MEMS sensors can be put on the put together, and that can work as a sensor, pressure sensor. So that is possible, but it's a long way to go. But that is a possibility, and that will give you a better response.
I can see in your problem statement, you also mentioned many points. But one of the point is, as you were discussing before we start the presentation, it was about the data collection.
Yeah.
Huge data is required to be collected to get these things validated.
Yeah. Very large amount, because if there are the different reasons why a person is getting blood pressure. Yeah, there are different. Some may be stress, some may be because of his internal disorders, etc., etc. But then Nadi Vaidya says that it's okay that you are having. The expert Nadi Vaidya doesn't ask you any questions also. He says that you are having this and this thing, and you have these symptoms. So he gives his medicine accordingly. but to have it objectively,
Yeah.
subject is okay. We do not have that information in brain. So to collect that information, which goes into the I mean, it's a practice, or it's the Nadi Vaidya's practice, and number of patients he is diagnosing and all that thing. He has all that information in his mind.
I wish to add that in Nadi Pariksha, actually, there is a more virtue and wisdom than the instrumentation.
Yeah.
He applies his virtue and wisdom more than the instrumentation, actually, sensing. Any more questions?
Yeah.
Please.
May I like to sum up, or if there are no questions?
Hello, can I ask one question?
Yeah, you can go ahead.
मी मनीषा खळदकर, शारदा शक्तीतर्फे. खूप छान झालं लेक्चर. मला एक प्रश्न असा विचारायचा होता, तो म्हणजे हे मेजरमेंट, हे क्वालिटेटिव्ह जे आहे ते क्वांटिटेटिव्ह करता येईल का? जसं आपण स्टँडर्ड कर्व करतो तसं जर पेशंटचा डेटा ऑलरेडी स्टोअर्ड असेल तर त्यातनं क्वांटिटेटिव्ह डायग्नोसिस करता येईल का?
हो, येऊ शकेल. पण ते डेटा आधी अवेलेबल असायला पाहिजे. तर नाडी वैद्य ज्या वेळेला तुम्हाला बोलवतात त्याला फर्स्ट they say that it's प्रकृती and विकृती. The प्रकृती is when you are ते सकाळी तुम्हाला बोलवतात मॉर्निंग without any food and anything, and that gives that in the morning you can check the prakriti of a person, and as सूर्य उगवल्यानंतर त्याच्या ह्यानी वगैरे तुमची विकृती वाढत जाते. So whenever the diagnosis is done, the disease diagnosis, so he has to have all this prakriti data with him, and on the basis of that basic prakriti what you have, then he can go for, if you are basically kapha dominant or pitta dominant, and over and above that, if there is some disease or some change, he sees that. So prakriti and vikruti are two things which need to be. But if you want to make it an objective information, you need a very large amount of data. That's what my prediction is.
थँक्यू. म्हणजे जे फॅमिली डॉक्टर ही जी कन्सेप्ट आहे त्यात जर फॅमिली डॉक्टर कडे हा डेटा अवेलेबल असेल तर इट विल हेल्प. थँक्यू.
जावडेकर जी, तुम्ही काहीतरी विचारायचा प्रयत्न करताय.
हो. ऍक्च्युली मला विचारायचं होतं की अशा टाईपची टेक्नॉलॉजी वेगवेगळ्या अवयवांना वापरली जाते का, किंवा वापरली म्हणजे जाता येईल असं मला म्हणायचं, वेगवेगळ्या अवयवांसाठी, हार्ट, किडनी, ब्रेन.
हो. पण I mean that as I said, we need a data. We can initially go for two very common diseases, but further we can add on how many diseases we can diagnose and all. But first thing is to translate the objective data into a subjective or subject to objective. That correlation has to be done.
ओके. म्हणजे येऊ शकतं, समजा हार्ट साठी किंवा ब्रेन साठी वापरायचं झालं तर येऊ शकतं.
हो, येऊ शकतं.
थँक्यू.
नमस्कार मॅडम, मी दीप्ती बोलते, दीप्ती देवबाकर. झालं सगळं लेक्चर, बरंच काम झालंय. मला असं म्हणायचं होतं की जेव्हा आपण बायोलॉजिकल सिस्टीम्स बघत असतो ना, तेव्हा रिलायबिलिटी, रिपीटेबिलिटी फार महत्वाची होते, कारण व्हेरिएबिलिटी खूप असते ना. तर ह्या आपल्या सेन्सरमध्ये तुमच्या एक्सटर्नल इन्फ्लुएन्स किती येऊ शकेल, आणि ही व्हेरिएबिलिटी कमी करण्याचं काय, म्हणजे आपल्याला काय करता येईल? तुम्ही दोन गोष्टी सांगितल्या, पण म्हणजे त्या दृष्टीने तुम्ही कसे प्रयत्न केले ते जाणून घ्यायचं होतं.
म्हणजे सेन्सर्स, तुम्हाला लार्ज नंबर ऑफ सेन्सर्स आम्ही डेव्हलप केले आणि त्याच्यातले सिलेक्ट केले. वन्स यू हॅव ऑल दिस ऑप्टिमाइज्ड, तर मग तुम्हाला लार्ज नंबर मध्ये मॅन्युफॅक्चर करता येतील. पण ते मॅन्युफॅक्चरिंग पर्यंत जायचं, जे इनिशियल एक्सपेरिमेंट, इनिशियल गोष्टी असतात त्या आम्ही ऑन स्मॉल स्केलला लॅबमध्ये केल्या की ते व्हॅलिडेट करून घ्यायचे सेन्सर्स किंवा
राईट, प्रूफ ऑफ कन्सेप्ट सारखं तुमचं खूपच छान झालंय. नक्कीच. या पण ऍक्च्युली ते आता म्हणजे आपल्याला जर ते तपासायचंय वापरायचं म्हणजे इफ यू वॉन्ट टू गो टू दॅट स्टेज विच इज व्हॉट यू आर सेइंग, सो रिपीटेबिलिटी, कारण इफ यू मेजर ऑन द सेम पर्सन number of times and you do the analysis, so you know variations that you get, those kind of issues I was talking about. And second, the external influence, how to insulate the device from the other external influences.
Madam, I
My
think you have covered that pulse rate and breathing and frequency of AC mains.
हा एक्सटर्नल इन्फ्लुएन्स होता तो एक ब्रिदिंगचा एक होता आणि 50 सायकलचा इनपुट. त्याच्यानंतरचे बाकीचे कुठले नाही येऊ शकणार कारण 50
Consistency दाखवता आली
सायकलचा
त्याच्यात.
ती अवॉइड केली. ती 50 सायकलचा आम्ही नॉच फिल्टर लावला आणि तो 50 सायकल गायब झालं त्यातनं. कारण आपण जरी तुम्ही बघितलं तर ऑसिलोस्कोपला तुम्ही त्याच्यावर टच केलं तर तुम्हाला 50 सायकलचं दिसतं बिकॉज यू आर द रिसिव्हर्स ऑफ 50 सायकल इलेक्ट्रिकल ज्या वायर्स जातात वरनं. आता जरा कमी झाला त्यामुळे तो गोष्ट कमी येईल पण तरी सुद्धा तो गेला आणि ब्रिथिंग फ्रिक्वेन्सी जी असते त्याचा इफेक्ट होऊ शकतो म्हणून त्याला ती लो असते खूप 0.2 हर्ट्स वगैरे असं काहीतरी आहे त्यामुळे तो खालचा डेटा आम्ही काढून टाकला आणि वरचा 50 हॅकलचा जो टिप होती तो काढून टाकला. आता 50 हर्ट्सचा खूप पुढे जातो पण तरी सुद्धा त्याची साब येऊ शकतं त्याच्यामध्ये म्हणून तो काढला.
ओके, थँक्यू मॅडम.
I think we are nearing.
तुम्हाला डेव्हलप करायला सगळं. थँक्यू.
We are nearing 11 o'clock.
Yeah, we are nearing to the end.
So I'd like to summarize the things.
Yeah.
It was a very good presentation, technical presentation, and moving forward, I think there are a lot of problems which researchers are feeling. In case of this Nadi Pariksha, my suggestion will be that there should be a joint meeting with Anirudh Joshi, who has developed Nadi Tarangani. And I presume that there must be some good points in Nadi Pariksha which can be incorporated, from Nadi Pariksha into Nadi Tarangani. And some kind of joint collaboration if it is done. Because otherwise there will be two products, competing with each other. And a lot of problems which are already facing in terms of funding, getting researchers, collecting data cannot be solved so easily. So my suggestion will be that there should be a joint meeting with, and then some good points which are there in Nadi Pariksha can be patented in the Nadi Tarangani, and whatever, money, etc., can be exchanged in terms of giving the knowledge of Nadi Pariksha in Nadi Tarangani. That is my suggestion. Otherwise, I don't think you can take it forward with so many other problems which you are facing. And one more suggestion was that incorporation of AI, which analyzes a lot of patterns, can also be done. But so these are the two suggestions that we should be having collaboration with Nadi Tarangani, and whatever good points are there can be patented in Nadi Tarangani, and the funding, etc., can be exchanged. So with that, if you got anybody else has got any points, we can conclude it. Otherwise, it's 11 o'clock.
Yeah, it is 11 a.m. already. So I think we should sum up with the thing. Thank you, madam. Thank you, everybody who are attending the program.
Thanks a lot.
Yeah.
Thanks a lot for giving me an opportunity.
Yeah. Thanks, Agarwal ji.
Thank you. Okay, bye.